Every mechanic has that one engine they refuse to work on, the one that makes them shake their head and quote double rates just for the aggravation, the one where fixing one problem creates 3 more. In 1997, Evinrude launched the Fitch direct injection system with promises of revolutionary efficiency. Within 2 years, powerheads were exploding at such rates that warranty claims nearly bankrupted the company. Dealers stopped selling them. That engine represents everything that can go wrong when good ideas meet terrible execution. Today, we're counting down 12 boat engines that were absolute disasters. Engines where the only good decision was walking away. Let's dive into the wreckage. Number 12, the diesel that got one thing wrong, the Yanmar 3GM and 2GM series. These engines earned legendary reputations for reliability across decades of production. Thousands of sailboats depend on them. Then one production run got the exhaust elbow design wrong and suddenly bulletproof engines were overheating and cracking heads. The problem centered on the exhaust elbow where water injection meets hot exhaust gases. Yanmar changed the casting design to save weight or reduce costs. The new design created hotspots that led to corrosion. The corrosion led to water intrusion. Water intrusion led to overheating. Overheating cracked cylinder heads. Owners discovered the problem when their reliable Yanmars suddenly started running hot. By then, damage was done. Cracked heads required expensive repairs. Some engines needed complete rebuilds. The irony was brutal. Engines known for lasting decades were failing after hundreds of hours because of one flawed component. Yanmar eventually corrected the design and returned to the proven elbow configuration. Engines from the problem batch can be fixed by replacing the elbow with the correct design, yet the damage to Yanmar's reputation lingered. When bulletproof engines fail from design flaws, customers lose faith. The 3GM and 2GM story shows that even legendary manufacturers can stumble. One bad component in an otherwise excellent design creates disasters. Owners of these engines from the affected years learned to replace the exhaust elbow preemptively rather than waiting for failure. Number 11. When fuel injection went horribly wrong. The Volvo Penta 3.0-litre and 4.3-litre GXI early fuel-injected versions. Volvo tried to modernize their reliable workhorses with electronic fuel injection. The result was engines that frustrated owners so badly that many converted them back to carburetors. The ECU failures plagued these engines from the start. The engine control units were sensitive to voltage fluctuations, moisture, and vibration. Marine environments are harsh on electronics, and Volvo's early ECUs couldn't handle the conditions. When the ECU failed, the engine stopped running. Replacement ECUs cost hundreds of dollars and often failed again. Hard starting became chronic. The engines would crank but refuse to fire. Sometimes they'd start cold and die hot. Other times they'd start hot and die cold. The fuel injection system would vapor lock in warm weather, injectors would stick, fuel pressure regulators would fail. Diagnosing problems required specialized equipment and extensive troubleshooting. Many owners gave up and converted the engines back to carbureted setups. The base engine architecture was solid, proven over years of reliable service. The fuel injection system was the problem. Removing it and installing carburetors solved most issues immediately. Volvo eventually improved the GXI systems with better ECUs and more robust components. Later versions work reliably. Yet the early models damaged the product line's reputation. When customers convert your modern fuel-injected engines back to carburetors from the 1970s, you know something went seriously wrong. Number 10. The oil injection system that destroyed engines. The Johnson and Evinrude VRO system on 2-stroke outboards. VRO stood for Variable Ratio Oiling, a system that promised to eliminate pre-mixing oil and gas. Instead, it delivered blown powerheads when the oil pump failed and owners didn't notice until catastrophic damage occurred. The concept seemed reasonable. An engine-driven pump injects oil into the fuel system at ratios that vary with RPM and load. Low speeds get less oil. High speeds get more oil. The system monitors itself and adjusts automatically. Owners just fill separate oil and gas tanks. The execution failed. The VRO pumps would fail without warning. Sometimes they'd stop delivering oil completely. Other times, they'd deliver insufficient oil. The engines would continue running until the lack of lubrication destroyed bearings, scored cylinders, and seized pistons. The warning system was inadequate. A horn would sound when the oil reservoir ran low, yet by then damage might already be occurring. The pump could fail mechanically while the reservoir showed full. Owners had no way to know the pump stopped working until the engine seized. Mechanics learned to hate VRO systems. Savvy owners disabled them entirely and returned to pre-mixing oil and gas manually. OMC eventually offered VRO delete kits. The market spoke clearly. Customers preferred the minor inconvenience of mixing oil over the major disaster of seized engines. The VRO disaster damaged OMC's reputation during years when the company faced other challenges. When your innovation destroys customer engines, trust evaporates. Johnson and Evinrude eventually recovered with better systems, yet VRO remains a cautionary tale about automation that fails catastrophically. You think oil injection failures were bad? Wait until you hear about what happened when Mercury tried to revolutionize two-strokes. Number 9. When Mercury's innovation had growing pains. The Mercury Optimax 150 through 250 horsepower first-generation models. The Optimax direct injection system represented genuine innovation in two-stroke technology. The early versions were nightmares of air compressor failures, injector problems, and ECU faults that left owners stranded and dealers overwhelmed with warranty work. The air compressor system was the primary villain. Optimax uses compressed air to atomize fuel during injection. The compressor is belt-driven and runs constantly. Early compressors would fail prematurely, leaving the engine unable to inject fuel properly. The engine would run rough, lose power, or refuse to start. Replacement compressors cost over $1,000. The injectors themselves caused chronic problems. They'd clog with deposits. The seals would fail. The solenoids would stick. Direct injection requires extreme precision, and early Optimax injectors couldn't maintain it. Engines would develop misfires, run unevenly, or lose cylinders entirely. The ECU software had bugs that caused bizarre behavior. Engines would go into Guardian mode for no apparent reason. Fault codes would appear and disappear randomly. Reprogramming the ECU required dealer equipment and updated software that sometimes created new problems while fixing old ones. Mercury stood behind the warranty and eventually fixed the platform. Later, Optimax engines from 2002 onward are significantly more reliable. The company learned from the early failures and improved components throughout the system. Yet owners of first-generation Optimax engines lived through years of frustration before Mercury got it right. The Optimax story shows that innovation requires iteration. The direct injection concept was sound. The execution needed refinement. Customers who bought early paid the price for Mercury's learning curve. Number 8. When Honda's advanced technology backfired. The Honda BF225 during the early VTEC years. Honda's reputation for reliability made the BF225 block casting issues especially shocking. Exhaust corrosion led to water intrusion, which led to engine failure. Expensive fixes hit owners even on low-hour motors that should have been trouble-free. The problem originated in the block casting around the exhaust passages. Honda's design allowed exhaust gases and cooling water to pass very close to each other. The castings developed porosity in specific areas, creating pathways for water to enter the exhaust passages. The water would corrode the passages from inside, eventually breaking through into the block. Water intrusion into the block caused immediate catastrophic problems. Hydrolock could bend connecting rods, corrosion would damage cylinder walls. The cooling system would lose pressure. Engines that seemed fine would suddenly develop serious internal damage. The cruel part was timing. These failures often occurred between 500 and 1,500 hours after the warranty expired, yet before owners expected major problems. A 5-year-old BF225 with 1,200 hours should be in its prime. Instead, owners faced repairs costing thousands of dollars. Honda eventually acknowledged the problem and extended coverage for affected engines. The company improved the casting process and redesigned the exhaust passages. Later, BF225 models don't have these issues. Yet the damage to Honda's reputation lingered. When the most reliable manufacturer in the industry has catastrophic block failures, customers notice. The BF225 failure demonstrates that even manufacturers with stellar reputations can produce problem engines. Honda's response, extending coverage and fixing the design, helped maintain customer trust. Yet owners who lived through the failures remember the experience. Number 7. When Suzuki's two-strokes struggled. The Suzuki DT two-stroke series from the late 80s through the 90s. These engines suffered from corrosion issues, ignition problems, weak lower units, and poor parts availability. This era was simply not Suzuki's finest hour in the marine market. The corrosion problems were systemic. The powerheads would corrode around mounting points, water passages, and anywhere dissimilar metals contacted. The lower units corroded through castings. Fasteners would seize from corrosion, making service nearly impossible. Suzuki's corrosion protection during this period couldn't match competitors. The ignition systems failed frequently. CDI boxes would die without warning. Stators would short internally. Trigger mechanisms would fail. These ignitions were sensitive to voltage irregularities and moisture. Marine environments killed them prematurely. Replacement parts were expensive and often failed again within seasons. The lower units earned reputations for weakness. Gears would strip, bearings would fail, the shift mechanisms would break, water seals would leak, allowing water into the gear oil. Mechanics learned to warn customers that DT lower units needed frequent attention and eventual replacement. Parts availability became a nightmare. Suzuki's dealer network was thinner than Mercury or Yamaha. Many parts had to be ordered from Japan with long lead times. Some parts became unavailable entirely as Suzuki discontinued support for older models. Owners found themselves unable to repair engines that might have been fixable with available parts. Suzuki eventually improved their marine outboards dramatically. The 4-stroke DF series from the 2000s onward are excellent engines. Yet the DT era damaged Suzuki's marine reputation so severely that many boaters still avoid the brand based on memories from that period. If you thought Suzuki had ignition problems, just wait until you see what Yamaha did with their high-pressure system. Number 6. When high-pressure direct injection became high-pressure problems. The Yamaha HPDI series, especially the 200 through 250 horsepower models. Mechanics call these engines grenades because of scored cylinders, failing high-pressure fuel pumps, and VST filter problems that left owners stranded and facing expensive repairs. The high-pressure fuel system was revolutionary and problematic. HPDI injects fuel at pressures exceeding 1000 psi directly into the combustion chambers. This requires precision pumps, precise injectors, and fuel cleanliness that marine environments struggle to provide. When the system worked, it delivered excellent performance and efficiency. When it failed, repairs cost thousands. The high-pressure pumps would fail catastrophically. Internal components would wear, reducing pressure. Seals would leak, contaminating oil with fuel. The pumps would seize completely. Replacement pumps cost over $2,000 plus labor. Many HPDI engines needed multiple pump replacements over their lifetimes. Scored cylinders became epidemic. The direct injection system required precise fuel delivery for lubrication. When injectors partially clogged or the high-pressure pump weakened, fuel delivery became inadequate. Without proper lubrication, the pistons would score the cylinder walls. Once scored, the engine lost compression and required power head replacement or rebuilding. The VST filter problems compounded everything. The vapor separation tank includes a fine filter that protects the high-pressure system. This filter would clog with debris, starving the high-pressure pump. The engine would lose power or refuse to run. Replacing the filter temporarily fixed things until it clogged again. Yamaha eventually discontinued HPDI and moved to 4-stroke engines. The company learned that high-pressure direct injection 2-strokes created more problems than benefits. Owners of HPDI engines faced ongoing maintenance challenges and expensive repairs that 4-stroke alternatives avoided. Number 5. When the second generation stumbled. The Evinrude E-Tech G2 during the early years. Great idea with rough execution. Early G2 models had steering failures, injector problems, and electrical gremlins that frustrated owners who expected Evinrude's latest technology to work flawlessly. The electric steering system failed on early G2 models. The actuators would malfunction, leaving engines stuck in one position. The control modules would lose calibration. The connections would corrode. Steering failure on the water creates immediate safety hazards. Evinrude issued service bulletins and replacement parts, yet the problem persisted through multiple production years. The injectors caused chronic problems similar to earlier E-Tech issues. They'd clog with deposits, the solenoids would stick, the spray patterns would deteriorate. Direct injection demands extreme precision, and early G2 injectors couldn't maintain it reliably. Engines would develop rough running, misfires, or complete failures. Electrical problems plagued the G2 platform. Harness connections would corrode, control modules would fail, the CAN bus communication system would develop faults. The sophisticated electronics that enabled G2 features also created new failure modes. Diagnosing electrical issues required dealer-level diagnostic equipment and extensive troubleshooting. BRP, Evinrude's parent company, worked through these problems with updates and improved components. Later G2 engines are more reliable, yet the early years damaged the platform's reputation right when Evinrude needed success. The company's decision to discontinue all Evinrude production in 2020 meant G2 engines never got the chance to prove themselves long-term. The G2 story shows that even advanced technology from experienced manufacturers can struggle during introduction. Evinrude had decades of two-stroke expertise, yet the G2 platform had teething. Problems that hurt customer confidence during critical years. But the G2 problems were nothing compared to what happened with the original Fitched system. Number 4. When Evinrude's innovation destroyed the brand. The Evinrude fixed early models from 1997 through 1999. These engines were so catastrophically unreliable they helped sink the company. Powerheads blowing up, injector failures, and ECU issues created warranty claims that overwhelmed OMC financially. FICT stood for Fuel Injection Clean High Technology, promising the future of two-stroke outboards. Instead, it delivered nightmare-level failures. The direct injection system was too complex for the technology available in the late 90s. Computers weren't fast enough. Injectors couldn't maintain precision. Fuel system components couldn't handle the demands. The powerhead failures were spectacular. Engines would seize without warning. Pistons would score cylinders. Connecting rods would break. These weren't high-hour failures from wear. These were catastrophic failures on engines with hundreds of hours. Owners would be running normally when the engine would suddenly destroy itself. The injector problems were epidemic. FICT injectors operated at high pressures with precise timing. They'd clog with deposits. The seals would fail. The solenoids would malfunction. A single failed injector could damage the engine by creating a lean condition in that cylinder. Replacing injectors became routine maintenance rather than occasional repair. The ECU issues created bizarre electrical problems. Engines would start and immediately die. They'd run at partial power with no fault codes. They'd go into Guardian mode for reasons the diagnostic software couldn't identify. Reprogramming ECUs became standard procedure, yet the software updates often created new problems. OMC's warranty costs from FICT engines contributed to the company's bankruptcy in 2000. The financial burden of fixing or replacing thousands of failed engines was unsustainable. When a single product line generates enough warranty claims to bankrupt a century-old company, that's a disaster on a historic scale. Bombardier acquired OMC's assets and eventually developed E-Tech technology that worked. Yet FICT remains the cautionary tale of innovation rushed to market before the technology was ready. Number 3. When cheap became expensive. Force outboards through their various ownership changes from Chrysler to Berliner to Brunswick. Often called the Yugo of outboards because of cheap materials, poor quality control, weak ignition systems, and short lifespans that left owners wishing they'd spent more initially. Force engines were budget options sold through discount channels and boat package deals. The initial purchase price looked attractive compared to Mercury, Yamaha, or Honda. The long-term costs were brutal. These engines nickeled and dimed owners with constant repairs and early failures. The materials were substandard throughout. Aluminum alloys corroded rapidly. Plastic components became brittle and cracked. Gaskets and seals deteriorated quickly. Fasteners seized from corrosion. Everything about force construction felt cheap because it was cheap. The ignition systems failed constantly. CDI boxes would die. Stators would short. Trigger mechanisms would fail. These weren't high-hour failures. These were failures on engines with 1 or 2 seasons of use. Replacement ignition components cost hundreds of dollars and often failed again within a year. The powerheads wore rapidly. Cylinder walls would score. Bearings would fail prematurely. Compression would drop. A Force engine with 500 hours often showed wear that a Yamaha wouldn't show at 2,000 hours. The internal components couldn't handle sustained use. Parts availability was terrible and got worse after each ownership change. Finding parts for older Force engines became nearly impossible. The engines were too unreliable to keep running, yet parts to repair them didn't exist. Many Force outboards ended up as boat anchors because repairs became impractical. The Force story validates the old wisdom that cheap tools cost more in the long run. Saving $1,000 on initial purchase led to thousands in repairs and early replacement. Boaters who bought Force learned expensive lessons about false economy. Think Force was bad? This next engine managed to fail in ways that still confuse mechanics today. Number 2. When Ford met Marine and nobody won. The Mercruiser 470 using a 3.7-litre combination of Ford 460 heads on an aluminum block. Everything that could go wrong did go wrong. Cracked blocks, chronic overheating, bad alternators, and failed cam seals. This engine represents what happens when compromised design meets cost-cutting. The fundamental problem was the block material mismatch. Aluminum blocks expand and contract differently than cast iron heads. The thermal cycling in marine use created stresses the design couldn't handle. The blocks would crack around cylinder bores. The head gaskets would fail repeatedly. The head bolts would pull threads from the aluminum. Overheating was chronic and progressive. The cooling passages were inadequate for marine use. The thermostats would stick. The water pumps were marginal. Once overheating started, it caused cascading damage that led to complete failure. Many 470 engines overheated themselves to death despite owners' best efforts. The alternator mounting was designed poorly. The alternators would fail from vibration and heat. The mounting brackets would crack. The belts would shred. Replacing alternators became routine maintenance on 470 engines. Some owners went through 3 or 4 alternators in a single season. The cam seals failed constantly, leaking oil into areas where it caused additional problems. The timing cover would leak. The oil pan would leak. These weren't slow seeps. These were significant leaks that left oil slicks behind boats and required constant monitoring. Mercruiser eventually discontinued the 470 and moved to more reliable engine platforms. The damage to Mercruiser's reputation lingered. Boats equipped with 470 engines became difficult to sell. Many owners repowered with different engines rather than continuing to fight the problems. The 470 shows what happens when engineering compromises meet real-world use. The design looked acceptable on paper. In practice, it created nightmares for owners and mechanics alike. You've seen 11 disasters. Now here's the one that mechanics still have nightmares about decades later. Number 1, the swing arm disaster that killed a company. The OMC C-Drive outboards with their infamous swing arm design. Weak lower units, brutal corrosion, near zero parts availability, and catastrophic failure rates made these engines the absolute worst disaster in outboard history. This single product line helped destroy Outboard Marine Corporation. The swing arm design eliminated the traditional lower unit with a complex mechanism that mounted the propeller on an articulated arm. OMC claimed improved handling and reduced drag. Reality delivered mechanical nightmares and failures that left owners stranded. The articulated lower unit was fragile beyond belief. The pivot points would wear rapidly. The seals would fail. Water would intrude into spaces that should stay dry. The shift mechanisms would break. The entire assembly would corrode. These weren't 1,000-hour failures. These were failures within the first season of use. The corrosion was spectacular. The aluminum alloys OMC used in C-Drive construction couldn't handle salt water. The castings would corrode through completely. The fasteners would seize solid. Components would corrode until they failed structurally. C-Drive outboards in salt water often didn't survive 2 seasons before corrosion rendered them unrepairable. Parts availability was non-existent from the start. OMC designed C drive with proprietary components that fit nothing else. When the system failed, which it did frequently, owners discovered that replacement parts either didn't exist or cost more than the engine was worth. Many C drive boats got repowered with conventional outboards. The warranty costs from C drive contributed significantly to OMC's bankruptcy. The company had to replace or repair thousands of failed engines. The financial burden, combined with reputation damage and lost sales, created a death spiral OMC couldn't escape. Mechanics refused to work on C drive engines, dealers stopped selling them, boat manufacturers stopped using them. The entire product line became toxic. When your product is so bad that your own dealer network refuses to sell it, you've achieved disaster on an epic scale. C drive represents the ultimate boat engine disaster. The concept was flawed. The execution was terrible. The results destroyed customer trust, bankrupted the manufacturer, and left owners with worthless engines on their transoms. What these disasters teach us. For boat owners, these disasters validate careful research before purchase. Established engines with years of proven service carry less risk than brand new technology. First-year models often have problems that get fixed in subsequent years. Cheap engines usually cost more long-term than quality alternatives. These engines also demonstrate that even reputable manufacturers can produce disasters. Honda, Yamaha, Mercury all have produced problem engines at various points. The difference is how companies respond. What disaster engine have you encountered? Did you own one of these nightmares or did you wisely avoid them? Share your horror stories in the comments and don't forget to subscribe. Thanks for watching.